So the law of conservation. First of all, let's review what we've done so far. I started out defining work. I said work was force times distance. Work is also the area under a force versus distance graph. We used that. Alex, could you shut that door behind you to keep the cold air that I'm trying to get in here? We said the problem with force times distance was, first of all, the force and distance had to be in the same direction, and you had to have a constant force. If I gave you a force versus distance graph, that could handle a changing force. You had to find the area underneath. Often it was a trapezoid, whatever. There's a better definition of work. First of all, we defined energy as the ability to do work, and this gives us the Work-Energy Theorem. The third, and honestly, the best definition of work. What does W stand for as a variable? No, that's as a unit. What does W stand for as a variable? I'll give you a hint. Thank you. Equals. Anyone? Anyone? What's a triangle mean? Okay, change in potential energy plus change in kinetic energy. And by doing that, now, Lydia, I've given you a work equation that also contains the 1/2 mv squared and the mgh, where what does change in anything mean? Okay. Yeah, Courtney, I cooled it off back there. Eric yawned. You're welcome. Okay. So you ready, John? Let's do this one together. It says a cyclist weighs 65 kilograms. His bike weighs 7.2 kilograms. Before we even start, John, so what's the total mass we're talking about here? Can someone go 65 plus 7.2? Anyone? Sorry? Okay, John, let's write that down. 72.2 kilograms. John, can you read to me the question sentence starting with the word how? And then read part A? So what does this question want me to find? Can you read to me the question sentence starting with the word how? Stop. What does this question want me to find? How much work? You okay with that? I thought I gave you a nice low ball there. Yes? It's not asking me to find speed. I think it tells me speed. It's asking me to find work. So all of us right now are going to write down the variable that we use for work, which is which letter, Trevor? Thank you. Equals. And then put your pencils down for 1 second. You may want your purple formula sheet out just so you can see the mental checklist you go through. So Haley, don't write this down. The first thing that I would try, John, is that. Did the question give me a force? Do you see newtons in this question? Did it give me a distance? Do you see meters in this question? So in my mind, I would cross that out, but that's the first checklist. I always try that for work first. Then I would see if they had given me a force versus distance graph. This is pretty obvious. Did they give me a graph in the question? But that's my next check. No. Pick your pencils up. Now I would go to the Work-Energy Theorem. Work is also the change in potential plus the change in kinetic. That's, Kevin, the checklist that we're going to do from now on. Sarah, whenever I see the word work from now on, force times distance, yay! Great, quit. Force times, no force, no distance. Graph, yay! Find the area. No? Okay. It's the change in potential plus the change in kinetic. And I'm not going to give you anything that can't be solved with those three. Change in potential, what we really think about here is a change in height. I don't think this question is giving me a change in height. I'm looking at this. I don't sense that. I think this is over flat level ground. So you know what the change in potential energy is here if there's no change in height? Nothing. Is that okay, John? Change in kinetic. John, what's change in anything? Thank you. I left it up there deliberately and made sure I didn't scroll down. So on my next line, I'm going to say this. KE final minus KE initial. John, what's the equation for kinetic energy? So final will be a half mv final squared minus, now I could have mv initial squared, but what is my initial speed in this question? So you guys okay? In this case, I'm going to do that. It's going to be 0.5, 72.2, 5 squared. This is how much energy it would take this cyclist to go from 0 to 5. This is how much work. You get 902.5 joules of energy. Is that okay, Courtney? Courtney, can you read part B to me? Still wants me to find how much work. So I'm still going to start out by saying, because the question was, how much work does it take for him to? Did they give me a force and a distance in this question, Courtney? Did they give me the area under a graph? Did they give me a force versus distance graph? Oh, then it's going to be change in potential plus change in kinetic. This is the work-energy theorem. If you do, really what it's saying is this, Haley, if you do work on an object, you're either changing how much stored energy it has, or you're making it speed up. Otherwise, you're not. Courtney, does this question imply any change in the height at all? So I'm going to do that. Courtney, what's change in anything? So this is going to be KE final minus KE initial. What was the equation? Oh, a half mv final squared minus a half mv initial squared. This time we're not starting out at 0. It's going to be 0.5, 772.2, 10, whoop, don't know how that happened, 10 squared minus 0.5, 72.2, 5 squared. Megan, this is something that's kind of counterintuitive. Megan, what's the difference between 0 and 5 meters per second? It's meant to be really easy as a number. How far apart are they? 5. What's the difference between 5 and 10 meters per second as a number? How far apart are they? But you're going to find you don't get the same answer. Not even close. This second answer is substantially larger. You get 2,707.5? In fact, if I divide that by the first answer, I find that my second answer is 3 times more energy. And this right here, Hedrick, answers a question you may have puzzled if you're curious. Hedrick, have you ridden a bike before? This is why once you get going fast, it's so much tougher to get going faster. To go from 0 to 5 meters per second takes 902.5 joules of energy, but for him now to double his speed again takes 3 times more energy. What if he wants to go another 5 meters per second faster? Alex, let's you and I look at part C. So in part C, what does it want me to find? You have to go all the way back to the top of the question. Work. W equals. Did they give me, well, it's force times distance. Did they give me a force or a distance? No. It's also the area under a force versus distance graph. Did they give me a graph? No. Then it's got to be change in potential plus change in kinetic. And again, Alex, we can say, woohoo. By the way, where does that energy come from? It's meant to be really obvious. It's got to come from somewhere. When you ride your bike, where does the energy that makes you go faster come from? Don't overcomplicate it. Does your bike have a motor? Where does the energy to go faster come from? You. Where does that energy come from? Your food. This is why you'll burn way more calories riding faster than you will riding slower. And riding twice as fast in this situation, you're not going to burn twice as many calories, 3 times as many calories. Thank you very much. This is why they're always talking about, in order to lose weight, high energy, high cardio, get your energy up higher. It's not just a linear relationship. It's because of that squared in the kinetic equation. Alex, what's changing anything? You know what? Let's take it. Let's just realize it's going to be a half mv final squared minus a half mv initial squared. It's going to be a half 72.2 v final 15 squared minus a half 72.2 10 squared. Again, notice, Courtney, it's another 5 meter per second increase. We went from 0 to 5. We went from 5 to 10. Now we're going from 10 to 15. So the increase in speed is the same each time, 5. We're going to get a way bigger answer here, too. Crunch this, see what you get. Don't all rush for your calculators at once, Cohen. I mean, all of you. What'd you get? 4,512.5? Hey, take that number, divide it by the 902.5. How many times more energy does it take to go from 10 to 15, 5 meter per second increase, than it does to go from 0 to 5? If I divide this one, is it 5 times more energy? In other words, if you rode at this speed, you'd be burning about 5 times more calories than riding at 5 meters per second. Not 3 times, 15 times, or 3 times 5 is 15, 5 times. The faster you go, the tougher it is to increase your speed. This explains why, please don't try this. This explains why you can't hold the gas pedal on a car down and just keep going faster and faster and faster and faster and faster and faster. Eventually, you reach a point where the amount of energy you need to increase your speed is equal to the output of the engine. Can't go any faster. Please don't try that. When my little brother was about 3 years old, my mom had left him in the car with the car running. He was in his car seat in the back seat, and she had ducked inside to grab something, and all of a sudden she heard the most horrible noise. My little brother had climbed out of his car seat, had flipped himself over the front seat, and had decided to hold the gas pedal down until it revved up so high that the engine just stopped working, that he blew a rod or so. If you don't realize how high an engine can rev, because it just sounds, it's just like, oh, what's going, and boom, he blew the engine. Anyways, so don't do that. My little brother, if he was a child now, would be classified as 80, 80, 80, H, H, D, 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 80, H, H, D, D, D squared. So anyways, love him to death. Let's do some rocket science. Sarah, what's this question? Example 2 asking me to find. Oh. How much work the engine did. How much energy the engine contributed to the system. Oh, well, work is force times distance. Clearly, I see a force in newtons somewhere, don't I? No? Okay. I do see a height, a distance, but I don't see a force. I'm going to abandon that. Is there a graph, a force versus distance graph? No? Then you know what? Work is the change in potential plus the change in kinetic. What's change in anything? Final minus initial. So this is going to be potential energy final minus potential energy initial plus kinetic energy final minus kinetic energy initial. Before we start plugging and chugging, let's pause. Are any of these, now by the way, it's important, don't get this mixed up with the law of conservation of energy. We use that when there's a change in height, change in speed, yucky curvy path, and they ask me how high or how fast. What did this question ask me, Matt? Work, okay. I know it has PE initial and PE final and KE initial and KE final. I know. Are any of these 0? Are we ever on the ground? Matt nodded his head. When? Of course. PEI gets hosed. Well, they're not really a province. Oh, sorry. Apologies to any of you from Prince Edward Island. But come on, it's a stinking island. It's not a problem. Anyway. Are any of these 0? Let's assume the rocket starts out at rest, because I've seen rockets and I haven't yet seen one that started out with a running start. So, how much work? This time, my equation simplifies to mgh final plus a half mv final squared. This is how much energy that rocket engine would have to supply in order to reach a height of 340 meters and in order to hit a top speed of 85 meters per second. If the rocket engine doesn't contain enough gunpowder to have that much energy, this can't be done. So we're just starting now, Trevor, to touch on rocket science. Now, it's much more complicated if you really want to go into space, but this is how you would start to calculate, hey, how much fuel do we need to pack? You'd know how many joules of energy there was per liter of fuel or whatever. The problem is as soon as you add a liter of fuel, you've also added more mass, so the M in your equation has changed, which means now you need more fuel, which means you've just added more mass again, so the M in your equation is it's a constantly changing equation. You really need calculus to do it properly. Calculus was designed to deal with equations that have more than one thing changing at the same time. 0.15. Matt, what's G? Negative? No, scalar. Height, 340. Plus 0.5, 0.15, 85 squared. You get 1,000, I'll go 1,040. Is that right? That's how many joules of energy must be contained in a little rocket engine. Stopping a car requires work. Do you know how I know stopping a car requires work? Because you have a change in energy. Courtney, am I wrong? Is my answer wrong, folks? No? Oh, okay. A 1,250 kilogram car, 1,250 kilogram car is traveling at 35 meters per second. About 100 and some kilometers per hour. Freeway speed. Lydia, what does part A want me to find? Okay. I like question A. I like question A. I like question A. Question A is a nice question. So Lydia, I would start out, and in my mind, don't write this down, I would, in my mind, write that. Can I find how much work using that? Did they give me a force? Did they give me a distance? No, but that's my checklist. I would say, okay. Did they give me an area under a force versus distance graph? No? Okay. Then I would move to the Work-Energy Theorem. Change in potential plus change in kinetic. Lydia, does this question suggest there's a hill at all? Say no. No. Okay. I don't think there's any. You can make a little arrow. No hill. Lydia, what's changing anything? So this is going to be KE final minus KE initial. Are any of these zero? Ah, what? You're right. Say it loud again. Final. I'm going to get a negative answer. Yeah, the car has to lose energy. It's not negative saying like down. It's negative saying you better lose some energy, otherwise there's no way you're able to come to a stop. Oh, the other way a car can come to a stop is by, this is what those emergency ramps on the sides of freeways are. You increase your potential because now your kinetic energy turns into potential energy. If you're losing kinetic energy, you have to come to a stop. But if we're on flat ground, we got to get rid of that energy some other way. Energy's got to come from somewhere. So we're going to get negative a half m 35 squared. Do you get that? Negative 765,625? No? Yes? No? Yeah? Okay. I'll write the whole thing. Negative 765,6 negative. Now, if you answered that as a positive, I'd accept it because the negative is telling me I have to lose energy. But if you're asking how much work we need to do to bring the car to a stop, we need to deal with 765,625 joules of energy. Oh, we need to lose that much. B. If it takes 82 meters to come to a stop, what force is required? Ooh. Cohen, what's B asking me to find? Force. What did we find, Cohen, in part A? Any suggestions? What, Prith? Could you maybe give me an equation I might want to write down? Ooh, he's even getting the F by itself already? Okay. Let's use our original definition of work, which had a force and a distance in it. Alicia, you okay with that? He divided by D to get the to get the F by itself. I was at a physics conference on the weekend, and they had a bunch of physics profs talking about kids going into first-year university physics, and they listed biggest problems, and number one was kids can't rewrite equations. They keep wanting to put in numbers. So I'm doing you guys a favor by making you put the numbers in last. I know it's a process, but I hope I've convinced you that it's such a better way to do it. So much less memorizing. How much work? 7,000. I'm going to ditch the negative. Cohen, what's the distance here? The other way to think about that negative is it's a direction for the force. If the car is going north, which way must the braking force act? What's the negative north? South. If the car is going east, the force to slow it down has to act east. The force, yeah. Wow, I thought I was doing a little Q&A. Okay, so that's another way to interpret the negative. 9,000, well, I'm going to go 9,340. 9,340 newtons. What's creating the force? Which force is this? Your brakes. By the way, where does the energy go? It's got to go somewhere. Yeah, it heats up your brakes. And the road a little bit. Okay. It's got to go somewhere. Can't just vanish. This is again why somebody I need to be looking at there, all you guys in the hallway. Did they go that way? So this energy, it's got to go somewhere, Ryan. Goes into heating up the cars. Electric cars bleed the energy off back into the recharging the batteries, which is one of the reasons electric cars are so much more efficient in the city. Every time you stop, you're gaining energy actually back for the battery. Very clever. How does that work? Take Physics 12. Ty, what's part C want me to find? What did we find in part B? Which force? Oh, this, okay. You know what? I think we'll do a quick sketch, but I think it's going to be reasonable to assume that if the car is moving to the right, we have gravity, we have normal force, friction is slowing it down. Remember, we talked about this. A car can move forwards with no force acting on it. In fact, if you're slowing down, the only force acting on you is backwards. Otherwise, you'd be speeding up. Ty, friction is what times what? Nope. Friction is what times what? Help them out, folks. Mu times the, yeah, you got formula sheet, right? Okay, let's write that down. I don't know the normal force. Oh, but look. I know the force the same size as the normal force. Which one? What's this question want me to find in part C? What's mu? I don't know. What's mu with you? How would I get the mu by itself? Boy, that seems very low. Let's put that a little closer. So if I hear you correctly, you're telling me mu is going to be, I'll write the full value now. Well, I'll write 9336.9. 9336.9. Again, I'm ignoring the negative. Haley, all the negative is telling me is friction is backwards, but I'm not using it in my calculations. What was the mass? 1250? G, 9.8. So I'm going to use my answer button. Whoa, my calculator shut off. Divided by 1250 times 9.8. I still have a negative in my answer. I'm just ignoring the negative colon. All that's telling me is, oh, it's backwards. Okay. Do you get a mu of 0.762? What are the units for mu, for the coefficient of friction? There are none. It's newtons over newtons, which just means they cancel. Okay? So I like this question. This is a nice, good review of forces here as well. Oh yeah, I guess you can turn the page. Now we can do accident investigation math. You might recall way back when, before Christmas, we did a question with RCMP investigating, but I really had to fake things. I had to say the cell phone had magically picked up the sound of the skid on someone's voicemail, and so we knew how long, we knew T. They normally don't have that. Here's what we can do. So it says this: an RCMP officer is investigating an accident. A car has struck a pedestrian at a school crosswalk. There are no witnesses, no cell phones that magically manage to record how long the accident lasted for. The officer measures the coefficient of friction at the accident site to be 0.65. They have a little device they do that with. And he measures skid marks that are 49 meters long. They have a tape measure they do that with. Should the RCMP press charges against the driver? What we want to do is reverse the last question that we did. We want to reverse the last question that we did. We're going to say this: work equals force times distance. Why can I say that? They did give me a distance. In particular, the work done by friction is going to be the force done by friction, the force of friction times distance. I should be able to, by looking at how long the skid is, I should be able to figure out how much energy the car had to get rid of. Oh, and Ryan, if I know how much energy the car had to get rid of, I can tell you how fast it was going. Minimum, because it might have stopped before skidding. It might have slowed down before skidding. With me so far? Ryan, friction is what times what? Yeah, it's the same free body diagram we did on the previous page. So I'm going to say it's going to end up being mu mg times d. Okay. Mr. Duke, they didn't give me the mass. Let's not panic. There's the work. What's the work-energy theorem? What's another way to write work? What did we learn today? Sarah, sorry, yeah, go ahead, Rye. Okay. Or change in potential plus change. It doesn't matter which order you write things in. Ryan, does this question imply there's a hill or anything like that? So you know? So I'm going to say this. Okay. What's change in anything? So this is going to end up being KE final minus KE initial. Yeah? Okay. Yes? Because your final in any car accident is always 0? Yes? So, this is also an expression for work. I'm going to ignore the negative. Ryan, look up, my friend. Is this work? Say yes. Is this work? Say yes. Is this work? Is this work? Then they equal each other. Right? Here it is. Mu m g d equals, except instead of kinetic energy, what can I write as an equation? And this will be V initial squared. Oh! Hey, did I need to tell you the mass of the vehicle? Turns out in car accidents, that's not that relevant. It's relevant, Cohen, in the amount of damage it does to the pedestrian on impact. It doesn't cancel there. But in terms of being able to calculate how fast you were traveling, nope. What am I trying to find here? What does the RCMP want to know? VI. How would I get the VI by itself? Times by 2? Now, finally, and it took most of the year to get there, but now we're doing some fairly authentic RCMP accident investigation physics. Looks like the minimum initial speed is going to be the square root of 2. I've scrolled down. What's mu, Ryan? I don't know. What's mu with you? No, what's mu in this question? Okay. G, 9.8. How long were the skid marks? Ryan? What? Oh, square root. It's going faster than sound? Almost bang on 25 meters per second. What's the speed limit in a school zone? 30 what? We need to convert this. How do I go from meters per second to kilometers per hour? Had something to do with the 3.6 times or divide. How fast was this guy going through the school zone? In fact, he's not just going to get ticketed. He might get prosecuted. He may end up serving jail time. This could be vehicular homicide, right? Or manslaughter. You guys played Monopoly? Yeah. Do not collect whatever. Yeah, okay. Go to jail. We can say this. Yes, the driver will be charged. Okay. By the way, I've scrolled back for a second. If you go twice as fast, what happens to the distance that it takes you to stop? Does it take you twice as long to stop? No? What, Connor? 4 times as long to stop. This is for all of you who are driving, because all of you are stupid drivers. I'm sorry, but you are. If you're going 3 times as fast, how much longer will it take you to stop? 3 times? No, 9 times further. Oh, and then please notice in the equation that coefficient of friction also appears. When it rains, the coefficient of friction goes down by about 50%, which means that also doubles the distance. Slow down when it rains. Put your pencils down. We're going to analyze a suicidal motorcycle driver. So from Loopy Motorcycle Rider, we have this. What can we find? Well, the first thing I'd like to find is how much work it took to bring him to a stop. I'd like to find how many joules of energy went into heat. Because that's, I think, where it went. Some sound, because you could hear it, but mostly heat. Did they give me a force and a distance? No. Did they give me the area under a graph? No. You know what? Megan, looking at the video, I don't think I saw a hill. Megan, what's changing anything? So the amount of work is going to end up being a half m v final squared minus a half m v initial squared. I did some Googling of, and looks like a standard bike and ride at roughly 300 kilograms. I took a guess. I Googled a few sport models that go fast. Clearly, he's not sitting on a dirt bike. Not if he's going, 350 kilometers per hour. So, okay. So it's going to be a half 300 45 is final. We are going to get a negative answer. Well, of course we are. He's losing energy. Minus a half, 300, 100 squared. Wow. I'm going to just write it as 1.2 million, but well, no, heck, let's keep this whole thing. 1196250, negative 1196250 joules. About 1.2 million joules. I don't know how big that is. That's tough for me to put into perspective. So I'd like to find how many watts of power were involved. Well, power is work over time. The work is 1196250 over, Connor, how much time elapsed? So I'm going to take this number. I'm just going to ignore the negative. What's a standard light bulb? Standard light bulb wattage. You've all put in a light bulb, I hope. Huh?
60.
How many light bulbs would this light? Divide by 60, or 1,208 60 watt. Now that energy is wasted. Are you seeing why electric cars are so much more efficient? Even if you can capture some of that energy. That's huge! That's a chunk of change there. Is this last one? Good, one more. I like example 4, I like example 4. Example 4 is a nice question. A rocket car is initially at rest on a frictionless horizontal surface. You know what? Horizontal means no change in potential energy. I might not even write that. Woo-hoo. The engine is ignited and the graph below shows the thrust force, F, versus the distance traveled, D, for the car. Why, just for food for thought, why do you think the force gets smaller after 15 meters? It's not a physics-y question, it's more of a rocket-y question. It's just burning out. By the way, Sarah, in real life, it would burn out with some kind of a curve. You guys don't know how to find the area under curves, so again, I'm in my magic physics world making the math work out nice. Take calculus. Okay. What I really like, Courtney, here is part B. Part B. Andy, what does part B want me to find? What? Okay, first of all, did I say velocity or did I say speed? Suggests a scalar. Maybe I'm going to think energy. What kind of a graph did they give me here? I'm thinking work. You know what? Let's write this down. Work equals Andy, does the equation for kinetic energy have a speed hidden in it? Yeah? Aha! I know where I'm going. We agreed we could do this. Andy, what's changing anything? this is going to be a half mv final squared minus a half mv initial squared. Oh, wait, Andy. Did they say that we started at rest? Ha-ha! You okay with that? Oh, Trevor, what's that letter stand for? Work. See this? I'm going to give you another way to think about it. That's what's going to go there. The area. Okay? In fact, I'm going to go like this. We're going to calculate the work. I'm going to call this rectangle area 1, and I'm going to call this little triangle area 2, and I'm going to tell you the work equals the area of shape 1 plus the area of shape 2. Andy, what's the equation for the area of a rectangle? Anyone, what's the equation for the area of a rectangle? What with it being math 7 and 8 and all? Width times height, length times width, base times height, side times side. Yeah, you know what? It's going to be 15 times 160. That times that. Yeah? Plus, Andy, what's the area of a triangle equation? By the way, if you want to, you can make a little note here. Length times width. What is a triangle? Base times height divided by 2. So in our particular example, the base is from 15 to 25, 10. The height is 160 divided by 2. How much work, how much energy did the rocket engine do, did the rocket engine give to this rocket car? Do you get 3,200? Anybody else? Yeah. That number can go right there. We can say 3,200 equals a half mv final squared. Andy, what am I trying to find here? How would I get VF by itself? Times by 2, divide by m, square root. Did they give me the mass? Please tell me they gave me the mass. Whew. By the way, you know what? I've just realized part B asked us to find the speed after 15 meters. Let's cross that out. We're finding the speed after 25 meters is really what we're doing. I just noticed there's a typo. I wanted 25 meters for there, and I was going to break this up into 2 parts. I'm doing this all in one big step. So it's really find the speed after 25 meters. So if I hear you correctly, the speed is going to be 2 times 3,200 divided by, what was the mass? How fast are we going? 2 times 3,200 divided by 5.2 square root. 35.1? Yeah. Is that okay? Yeah. You're not going to be getting more homework next class for the next lesson. I don't have a homework lesson attached. So you'll have time next class to work on this. But for now, my lesson went about 10 minutes longer than I want. For now, yeah, you can try. Every question.